I'm recording this from the Yao Math camp in Shanghai, honestly a super underrated camp with extremely talented people and extremely hard courses. But despite my limited time, with my channel on the rise, I just knew I had to make an entry to the 4th summer of math exposition. I had a lot of fun researching the math and making the visuals, so I really hope you enjoy. To start off, here's a simple neural network I made that trains off the classic MNIST dataset, which contains 60,000 training images of handwritten digits, and the network has the simple task of distinguishing them. It's not perfect though, at just over 97.5% accuracy, which means it gets under 1 in 40 wrong. I'll probably improve that in a future video where I also get to explain the entire thing. Anyways, each image in the dataset is 28 by 28 pixels, which means 784 inputs, which is pretty massive to think about. Now, you've seen the title of the video, so it's time to figure out what gives data in high-dimensional spaces this curse. Well, for a start, more dimensions means the space of our data grows rapidly. It's exponential or factorial. Algorithms will have higher runtime as well as storage requirements. Additionally, with this super large space, there's no way we'd have enough sample data to go through every region, so it's going to be pretty spaced out. However, we don't always need to. For instance, each of our digits has a standard shape that makes it look like itself, which means that most of our space will be empty with the exception of a few regions that represent each digit. Additionally, for machine learning algorithms, a problem called underfitting could occur where there isn't enough representation of trends, so our network just makes something up. The solution? Dimensionality reduction. Transform points, somehow, from high dimensions to low dimensions, preferably keeping as much information from the original as possible. To illustrate this, I'll use 2 dimensions, which are both easy to understand and animate. Suppose our data belongs to 3 classes, so we have 3 clusters of points like so. How do we project this from 2 dimensions to just 1 dimension whilst retaining lots of information? Let's start simple and say that we're only allowed linear projections, so we just choose a direction and draw a line for the points to fall on. Then, maybe something that comes to mind is to set the direction that maximizes the variance of the projected data. It does make sense, that direction should generally give us better separation, meaning more detail, so we could even go as far as to call it the principal component of our data. Since variance only depends on the relative positions of our data, let's normalize it along each dimension to make our calculations easier. This also has the effect of making the units arbitrary, so this balances out the size of different variables to make things fair. Let's say a point has position vector xi, and let's call our projection vector w. Again, to make calculations easy, let's make it a unit vector, so the magnitude of the projection is the dot product of w and xi. Then, using the definition of variance, let's square that and take the sum for all points to get the expression we want to maximize. A cool thing is that if we do a bit of fiddling, minimizing the square of the projection error turns out to be equivalent to what we're doing here, which is a good gut check that we're doing something right. Back to maximizing. The first thing we can do is to replace the sum of dot products with a single matrix vector product, x times w. Here I want to introduce something called the transpose of a matrix. It's very simple. Basically, it's an operator that flips the matrix over the diagonal starting from the top left. Just swap the rows and columns. X times w is a column vector, and we want the sum of the squares of its entries. Well, that's just equal to xw transposed times xw. What next? Well, a property of transposes is that when we take the transpose of a matrix product, then it's the same as taking the transpose of the individual matrices while reversing the multiplication order. This turns the transpose of xw into w transpose times x transpose. It turns out that the matrix 1/n times x transpose x has a special name, the covariance matrix of x. If you have no clue what that means, and I didn't either, the covariance sort of measures the direction of the relationship between 2 variables. And if you have 2 random variables, x and y, it's defined as the expected value of x minus its mean times y minus its mean. We can fiddle with this to write it as the second expression here, which lets us ignore the second term since we've normalized and the means are just 0. To see how it works, take a look at these plots. In the first one, you mostly get positive times positive or negative times negative, resulting in an overall positive covariance. While in the second, most plots have coordinates with opposite sign, and covariance will be negative. In the third, it's just about 0. The covariance matrix shows the covariance between all pairs of variables, and I'll write it as S. Okay, there's just one more step to find W, and it's a big and exciting one. We want to maximize the value of W transpose times S times W with a constraint that W is, of course, a unit vector. A strategy that I learned to solve these constraint optimization problems is Lagrange multipliers. Sounds fancy. Let's write a constraint as an equation with the matrix transpose, so W transpose times W equals 1. Lagrange multipliers work like the following. We have an optimization problem where we want to find the maximum value of some function, say f, that takes in two inputs, x and y, with a constraint that some other function g of xy must be equal to a constant c. Let's have a look at this point on g here. If we take the gradient of f at that point, then it's going to point towards the right, towards the peak. So what happens when we move this point to the right? Well, the gradient is going to gradually change direction until there. It's pointing completely perpendicular to g now, so if we move any more to the right, we'd be going opposite the gradient. Not good. That means that at this point there's nowhere better to go without straying off the path, so it's our maximum. We know that the gradient of g gives the perpendicular direction of our curve because it tells us the best direction to leave it. That means that we want the point such that the gradient of f and the gradient of g point in the same direction, and we can write it as them being a scalar multiple lambda of each other. Let's use that equation to finally get a solution to our unit projection vector. Since I've yapped for a bit, I'll stop and let the working show for itself. Eigen jump scare. Who could have known? In order to maximize the variance of the projected data, W must be an eigenvector of S. Now that's a useful application if I've ever seen one. But which eigenvector though? There's multiple. The answer turns out to be the one with the largest corresponding eigenvalue. Why? The intuition is that the larger the projection, the more variance that vector carries, so we should naturally choose the one with the largest eigenvalue for the largest projection. Hang on though. Could this mean that the other eigenvectors are our other principal components? Well, indeed it does. We can show that all the eigenvectors are orthogonal to each other, meaning that they are valid principal components. So once we find all the eigenvector-eigenvalue pairs, all we have to do is to sort them by eigenvalue and take the first k eigenvectors for the first k principal components. And that's it, we're done and ready to project to a lower dimension. Let's do a principal component analysis on the MNIST dataset. As you can see, over 90% of the variance is explained by under the first 250 principal components. That's a significant reduction, so let's use those 250 to flatten our data to under a third of the dimension. While around 9% of the variance is lost, the network loses under a single percent of accuracy, but it's a lot faster. For fun, here's a 2D plot of digits with two principal components, amounting to a sad 9.7% of the total variance. Even so, we get to see some semblance of clusters. The problem with PCA that you might have noticed is that it's not suited at all to our problem because it doesn't focus on separating classes, it doesn't take in any labels at all. This is why PCA is just a pre-processing technique just to get rid of the correlation of our variables, which can benefit subsequent actual classification, which we'll explore in our next technique, To focus on class separation, let's for a start try to maximize the variance of the projected means or centroids of each class. Let's set the global centroids as m and the projected centroids as mu. Then the variance can be found as follows. Note that we weight each contribution by the size of the class, as it's of course better to separate a larger class than a smaller one. We can use our knowledge of the transpose to factor out the projection vector w. Then, since w is a constant, it'd be nice to have it outside of our sum, which we can do by taking the transpose of the second term in our square to flip the order. Transposing a 1x1 matrix has no effect whatsoever. At the end, our middle sum will be a square matrix called the between class scatter matrix, which is called that because we're comparing points to the overall mean instead of its class mean. It's actually very closely related to the covariance matrix we saw earlier, the only difference is that it doesn't have the 1/n. However, if we just focus on separating the centroids, we encounter a problem. Suppose the data is like this. Then, there ends up being a lot of overlap for the data if we just use the same direction as before. Therefore, we also need to minimize the variances of the individual classes. Then, for some class J, we can do a similar simplification with the means like so. At the end, this gives us the within-class scatter matrix, since we compare each point with its own class mean instead of the overall mean like before. So, since we want to maximize this first expression and minimize the second one, it makes sense to find the maximum of this fraction. To do that, we use something I never thought I'd see here, the quotient rule. When we were differentiating the Lagrangian when deriving PCA, we found that the derivative of W transpose SW is 2SW. So after applying the quotient rule, we have this, and after some rearranging, since f of w is a scalar, when we isolate f of w times w, we see once again that w is an eigenvector, this time of inverse of SW times SB. That was a lot faster than PCA, thankfully. And additionally, we can show that since the columns of SB are linearly dependent, it has rank less than its size, the number of classes, C, and has a maximum of C-1 eigenvectors. Let's now put this method into practice. So far, the two techniques we've seen are both linear transformations, which are useless in the face of data such as these concentric circles or this spiral. Also, both 2D visualizations haven't been great either. How can we get near-perfect plots like these? Well, this can be done with nonlinear methods, so I'll throw in the famous Created in 2008, T-distributed stochastic neighbor embedding is an improvement over the original stochastic neighbor embedding algorithm invented in 2002. Let's first go over SNE, then describe its issues and how tSNE deals with them. Being a nonlinear projection, SNE allows points in low-dimensional space to be placed with much more freedom. It does this by iteratively shifting the low-dimensional points to try and accurately reflect the relative distances between points in the high-dimensional space. First, it calculates the similarities between each ordered pair of points I and j, denoted pi to j. It does this by placing a Gaussian distribution around point I with its own standard deviation sigma I, which we'll see how to choose soon. To normalize these values, we divide each one by the total similarity around point I so that all the probabilities add to 1. Let's now call the mapped data points y. Then, we can calculate a similar measure of similarity q in the low-dimensional space, which we can compare with the original. The difference is that the variance of the low-dimensional Gaussians are all equal, which will simply give us a balanced output. The loss function that we're going to measure and optimize is called the Kullback-Leibler divergence. Notice how this cost is designed. If two points are close together in high-dimensional space, but far apart in low-dimensional space, then p is high and q is low, and we get a high cost. But the opposite case, when p is low and q is high, we only get a small cost. This shows that tSNE focuses more on local structure and doesn't care about accurate global geometry. At the start, we can place our points randomly around the origin. We can then optimize this cost function using gradient descent, which is the same as what my neural network does. If you're not familiar, in very short terms, if you want to find how to tweak your inputs to minimize some cost function, you take the derivative of that cost with respect to each input to figure out how much you should shift each input. Thankfully, the gradient of c with respect to each point ends up being quite simple to calculate, and can be thought of as a bunch of springs pulling on each point. The cost function, as stated by the authors, is difficult to optimize, and so they also use momentum and add random noise in their gradient descent, both to speed up the process and help escape local minima. This leads to needing to run tSNE multiple times while tweaking the parameters to get optimal results, which isn't great. I ran it a few times with the goal of producing a circle, and you can see the inconsistencies here. When I was reading the tSNE section of the paper, I was intrigued by the choice to have two different probabilities for the similarity of point I to j and point j to I. It seemed a bit complicated, but I ran with it. However, a variant that gets closer to tSNE is symmetric SNE, which has symmetric values of p and q. In low dimensions, we can replace the denominator with the sum of Gaussians for all pairs of points. In high dimensions though, this doesn't work as well because sometimes, for example with an outlier, this doesn't give us enough information to place that point. Instead, we simply set pij and pji to the mean of the two asymmetric similarities divided by n. This makes the symmetric similarities large enough to be significant while also being roughly on the same scale. In preliminary experiments, we observed that symmetric SNE seems to produce maps that are just as good as asymmetric SNE, and sometimes even a little better. Now to the biggest difference between SNE and tSNE. When mapping from high to low dimensions, as I mentioned in the beginning, space goes from very open to not so open. Thus, the ratio of points at a medium distance to points at a short distance will be much higher in high dimensions than low dimensions. Therefore, in low dimensions, those points at medium distance will have to be crushed together. This is known as the crowding problem. We could add a repulsion force to spread out the points, but there's a much better way, which is where the t-distributed in tSNE comes into play. Instead of a Gaussian in the low-dimensional space, we use a t-distribution with only 1 degree of freedom, also known as the Cauchy distribution. As you can see, the two tails of the curve are a lot taller, meaning that we can have moderately spaced points further away with good enough probability. Let's have a comparison between the gradient of SNE and tSNE. Straight away, you can see a big difference between them. While SNE has very weak repulsion forces compared to attraction forces, tSNE is good with both strongly attracting and repelling pairs of points, and will have much better accuracy in modeling faraway points with these long-range forces. This means the cost function becomes much more clear-cut and easier to optimize without adding random noise. But hold on, you never got to talking about how to choose the standard deviation for each high-dimensional Gaussian earlier. This variable is determined by a tunable parameter that we choose ourselves known as perplexity. The paper does not give nearly enough justice to how interesting the choice of this variable is, but it provides a starting point where we can explore. The perplexity of the ith point is defined as 2 to the power of the Shannon entropy of the high-dimensional probabilities. Entropy was interesting enough that I could devote a short segment to it, but there is only 9 days left, and so I'll just say it can be interpreted as the expected value of the uncertainty or surprise the outcome of a variable holds, and leave the rest to your interest. According to the paper, the perplexity can be interpreted as a smooth measure of the effective number of neighbors, and you can see that as we increase our variance, our probabilities converge closer to the entropy maxing uniform distribution, so perplexity increases accordingly. Let's see how our points move around under tSNE with different perplexities, with the target shape again being a circle. Let's tweak the learning rate first though, where I'm using a fixed perplexity of 20. I ran multiple trials and found that the results were quite consistent, which was already much more different from SNE, which didn't always produce the same results using the same parameters. Surprisingly enough, a lower learning rate of 5 seems to produce the fastest convergence. Now let's try changing their perplexity. For a lower perplexity of 10, we don't get a circle at all, the points just don't want to be clustered enough. For something like 15, it's better, but still takes really long to converge. But finally, with 25, we get a circle within 1,000 iterations. There's a really nice article I found with a lot more configurations that goes into detail on the properties of tSNE and choosing the perplexity value, which is super interesting. Before we try it on the MNIST dataset for real, there are some tricks that are used to bring out the full potential of tSNE. First is a major speedup using an adaptive learning rate scheme called the delta bar delta method. When the gradient is changing steadily, like a hill, we can increase our learning rate to get down faster, but when it fluctuates, we need to drop it to explore each dip to search for the best minima. Rates are increased linearly to prevent us from going too fast, while they are decreased exponentially to drop them quickly if needed. This turned out to be really effective, and we easily get to a circle within just 100 iterations. The second is early exaggeration. Very simple, you just multiply the high dimensional probabilities by some factor, say 4, in the first couple iterations, which heavily encourages points to come near the center to form clusters easily. You can clearly see the effect this has on our data points. Well, we've on the whole maxed out all the abilities of this technique, so let's... That's right. Calculating distances is hard work with so many dimensions, so how about we use PCA to reduce them first and then run tSNE?